Good day to each and everyone. So our topic is all about Hamiltonian and Eularian graph, Module 6, Section 2. So before we proceed what Hamiltonian about, I will discuss first what is Eularian is all about. So Eularian graph. The term Eularian graph has two common meanings in a graph theory. One meaning is a graph with Eularian circuit, and other is a graph with every vertex of even degree. A graph is made up of vertices and edges. Vertices are sometimes called nodes, and they're indicated with a black dot or circle. So, two vertices can be connected by more than one edge, sometimes called a multigraph. For example, this graph, for here these two vertices are connected by two edges, and these two vertices will be connected by three edges. Just because two edges cross does not mean there is a vertex there. So, like for example, in this graph right here, this edge crosses each other, but there is no vertex there. So, Euler. An Euler path visits every edge once. An Euler circuit or cycle visits every edge once and begins and ends at the same vertex. An Euler circuit is still an Euler path. It is a special type of Euler path. An Euler circuit is possible if every vertex has even degree. An Euler path is possible but an Euler circuit is not possible if exactly two vertices have odd degree. No Euler path is possible if more than two vertices have odd degree. In this first graph, a pairwise have 5 nodes and also have 10 edges. A Euler circuit is possible. And I know that is possible because if you take a look at each vertex, there are 4 edges coming over each of these 4 even number. So, in order to make the circuit, start here to the classic star figure. And this multigraph, we have an Euler path but no other circuit. This vertex has degrees 3, and this vertex have degrees 5, and this vertex have degrees 4. You need to begin and end your path and vertex with odd degree. And this third diagram has no Euler path at all way to add many-odd vertices. This graph does have a Euler path. So, the Euler path is CD, D to E, E to F, F to C, C to B, B to A to F. Eularian graphs and Eularian circuits. A circuit is a closed walk that repeats no edges. An Eularian circuit in a graph G is a circuit that passes through every edge in G. An Eularian graph is a graph that contains an Eularian circuit. So in this layout is intersection of the CD. The color of blocks are the buildings, and the spaces between them are the streets. There is the sort of problem that makes Eularian circuits and grows interesting. And of course, as a graph theorist, we can define as problem. As a graph theory problem, what we'll do is represent street as edges and will represent an intersection of streets as a vertices.
Today everyone, we will discuss about Hamiltonian graph. Hamiltonian graph is said to have circuit that visits each node or vertex exactly once with no repeats. It also visits every vertex once with no repeats but does not have to start and end at the same vertex. These Hamiltonian circuits are named for William Rowan Hamilton, who studied them in Athens. So, Hamiltonian cycle, path and graph travels exactly once over vertex in a graph is called Hamiltonian. In summary, Hamiltonian graph is composed of multiple vertex lines that can possibly be visited once in a path. So as you can see in the picture, it is an example of Hamiltonian graph where the vertex or the yellow ones are visited once. Another example is that it has a 7 vertex, which if you can draw it or you can use a line to draw a line, it can possibly visited once. So therefore, this is an Hamiltonian path or a Hamiltonian circuit. Of it is that this Big Dipper constellation is like a Hamiltonian path but not a Hamiltonian circuit, because in the part of the line of the vertex of A, it is not visited once but it is visited twice. Another example is fish-like growing stick that is not a Hamiltonian path because at the tail of it, it is not visited once but it is visited twice, as you can see in the picture. View a theorem that can possibly recognize a Hamiltonian path. It is the Dirac's theorem. So, Dirac's theorem provides a sufficient condition for a graph to have a Hamiltonian circuit. So, basically, Dirac's theorem says that a graph with a greater than 3 vertices and every vertex having greater than half of the number of the vertices is Hamiltonian. So, basically, if I have this particular condition, meaning it has the condition having the number of vertices greater than 3 and every vertex having degree greater than half of the number of the vertices will be Hamiltonian. That is basically the sufficient condition for a graph to be Hamiltonian according to Dirac's theorem. For example, number 1. Let us say we have a graph like this. As you can see in the picture, it has 4 vertices, A, B, C, and D. Based on Dirac's theorem, we have more than 3 vertices. And let's check out the degree of each vertex. So, the degree of A is 3. Meaning, kung malantaw nimo na ay tulo ka linya gigunitan ang A parehas sa B, C, ug D nga vertex. Based on Dirac's theorem, if the degree of the vertices is greater than half of the number of vertices, the number of the vertices here is 4. Half of 4 is 2. Since every vertex is degree of 3, therefore, the degree of the vertices is greater than the half of the number of the vertices. Therefore, this particular graph should have the Hamiltonian circuit. As you can see, in this graph has the condition of the Dirac's theorem. Therefore, it has the Hamiltonian circuit. Example number 2. Let me give you another example. As you can see in this particular example, we have 5 vertices A, B, C, D, and E. Vertex A and vertex B have the degree of 3. Vertex E has degree of 4, and the vertex C and D, both of them has a degree of 2. Even though the condition of the Dirac's theorem does not apply in this particular graph, however, it is a Hamiltonian circuit because we can start from go to B, then to D, E, C, A, and end at B. As you can see our path is a circuit and it hits every vertex exactly once and starts and ends at the same vertex. It is Hamiltonian circuit or graph. But the condition of the Dirac's theorem is not present. So, as I mentioned at the beginning, when these Dirac's theorem conditions are present in a graph, it is sufficient for the graph to be Hamiltonian. However, if the condition is not present, not mean that the graph is not having a Hamiltonian, as we can see it in this particular example.